Hello, everyone. Welcome, presenters, and welcome to the audience. My name is Jasmina Burek, and I'm a postdoctoral associate at MIT. It is my pleasure to serve as a chair of the Solution and Technology session. We have 5 presenters today, and each presenter will share their screen. Each presenter has 10-minute time to present, followed by 5 minutes questions and answers. You can put the questions under the question mark ask button, and our presenters will answer as many as possible. So our first presenter today is Jianlong Bai, who is an interdisciplinary researcher and focuses on electrical machine design. Jianlong, take it away.
Okay, let's go. Hi, ladies and gentlemen. My presentation is integrated solution to carbon emission, plastic rubbish, bushfires, and wilderness reduction. We are facing 3 globally urgent issues, equally urgent, in fact, though carbon emission seems the most. As an interdisciplinary engineer, I research what I can touch, and my pleasure to share and discuss the solutions with you. Carbon emission has been leading to climate change, which results in many kinds of disasters, ecological disaster, catastrophic bushfire, and so on. My research started with the problem of South Australia blackout. There, for low carbon, renewable energy power plants substituting the thermal lead to sharp reduction of grid inertia or resiliency, the root of blackout. I provided the solution, a paper in 2019, and expanded my research.
Sorry to interrupt you, but you were out of the slide mode. Okay, now it's good.
And expanded my research to how to resolve carbon emission. This part is carbon-free water power grid configuration for getting zero carbon emission. And I found more than that. By collecting sufficient non-carbon energy, what the power grid or largish region power grid can provide the premise to upgrade metallurgy industry. Metallurgy, one of the main carbon emission sources at present, will not emit carbon anymore, but become oxygen maker. Here, power pipeline, the component of water power grid, and oxygen byproduct will relate to the next section, plastic rubbish disposal. The solution and technologies have been discussed in a particular paper, Zero Carbon Emission Based on Carbon-Free Water Power Grid, and the decisive technology converter train has been preferred. As to the upgraded steel making, hydrogen reduction probably is the most feasible method, or maybe aluminosemi, because a new method claims that 710 degrees is enough for aluminum electrolyzing production. This diagram of electrolyzing steel making comes from molten metal. Plastic rubbish has polluted everywhere of the globe surface, even our atmosphere, and resulted in another kind of ecological disaster, especially in the ocean. It's obvious that waste plastic disposal or management is a tough task, or else why plastic rubbish has been accumulating so many years. The existing disposal waste, besides limited recycle, There are three, basically. The first, waste energy incineration, high cost, too high. Second, open incineration, emit toxins, especially dioxin, unacceptable. The third, pile and pile, lose control of management sooner or later. After research, I suggest two viable ways. The first, zero emissions incineration. Oxygen is a byproduct, so it's cheap. With sufficient oxygen, almost all components of rubbish can combust completely. Plastic, resin, chemical fiber, rubber, metal, silicon, etc. can all mark in. After incineration, carbon dioxide is the main product. Via compressing, the gases can be separated and stored easily. By the way, do you know carbon dioxide can be electrolyzed? Sure, it can. I just know that a few hours. The second way is the installation of power pipeline we just mentioned in last section. According to estimation, power pipeline can recycle almost all waste plastic and rubber around the globe. We have well-known catastrophic bushfires in 2020, 4 months burning in Australia, some fires in Siberia, Russia, and California wildfires. This chart shows wilderness reduction vs population increasing in the past years. I've given the solution suggestion in the paper, including the key trans-upland water diversion. As here, in right side, there's pump chain. The left, turbine generators. When temporary surplus power emerges in water power grid, it can be used to pump water up to upland to get hydro storage. And then, when the grid needs more power, the stored energy will be released. And at the same time, the left side drought place gain water. For example, South Midwest drought with East abundant water in USA. So it's one stone to burn in benefit. Almost every drought place on the globe can gain the necessary or sufficient water to decrease or eliminate bushfire accidents, to turn deserts into farms and homes for wilderness recovery, and benefit the grid. Now, let's summarize. Solar, wind, and so on non-carbon energy around the globe can be collected by the power grid, then power out. By upgrading industry, low-priced byproduct oxygen can be gained and realize zero emissions incineration. The power grid construction will recycle almost all waste plastic and rubber. Frequent temporary surplus power from the power grid will improve our environment, including wilderness recovery. And with energy storage, water diversion will benefit the power grid. Finally, I'm confident that carbon-free world power grid will drive our globe goodliness in the future. Thank you.
Thank you so much for your presentation. Are there any questions from the audience first? So I have a question. So you were talking about the global carbon-free world power grid. What is the current efforts in China? Where does China see their opportunities to reduce their greenhouse gas emissions?
Precisely, I don't know very much about that because I'm not belong to any institution, research institution. In fact, I don't know very much about that. But I know the technology about one technologies that direct current transmission. Current DC direct current transmission on its problem. So I give my solutions, distinctive solutions. I believe you can judge it if you read my particular paper. Just like introduced in slide, zero carbon emission based on carbon-free world power grid. Okay.
Awesome. Thank you so much for your presentation. We're moving to the next presenter. Her name is Rachel Armstrong. Rachel Armstrong is a professor of experimental architecture at Newcastle University and is a visiting professor in regenerative architecture at Leuven, Belgium. She pioneers the concept of living architecture, where built constructions possess some of the properties of the living things. She will also be giving a key talk tomorrow on the ethics of this practice. So you're all invited to join the key talk at 11 a.m. Eastern. Rachel, welcome, and please take it away.
Good afternoon, everybody. I'm just still figuring out how to screen share the right screen. So, yeah, stopping screen share, sharing screen, and how do I pick up the right screen? Do I just click on the? I can't see how to get to the screen that I'm after. I have a presentation there, and it's yes. Thank you. Hello.
Okay, I'm back, and based on our tech, you just need to lower your Explorer or whatever the browser, and then yes, now we see your presentations.
Oh, okay, so now if I do full screen, you'll be able to see it.
Okay, yeah, let's make sure. I'll stay here.
Okay, tell me.
Yes.
Are we good? Thank you.
You're good. Thank you.
Apologies, everybody. It's a fantastic platform. I'm just very unfamiliar with it. So straight into it. Well, we live in a world of microbes, and over 99% of them are actively regenerating the environment. They're making nutrients available for our reuse, and they're enabling the growth of plants and the decomposition of bodies. Now, even before we could see them, we have welcomed microbes into our homes as part of our cultural practices of food preparation, cheese, bread, pickles, and yogurt. And they've also been used as farming workhorses in composting, fermentation, and tanning processes, which have been scaled to become industries. Now, the advent of advanced biotechnology approaches means that we can now garden and direct the incredible metabolic diplomacy of microbes in new ways. Now, while microbes are a natural and cultural part of our lives, they gained a bad reputation in the 19th century when Louis Pasteur and Robert Koch demonstrated that certain microbes were responsible for particular diseases. Equating them with contagion, we waged war against all of them, which characterized the modern reign of hygiene. And that banished all known germs from our homes using a range of techniques from chemical poisons to wipe clean surfaces. Now, going to war with microbes destroys our environment too. And if we are to establish a culture of life, then their co-constitutive capacity needs to be reinstated. So in this presentation, I want to concentrate on how we can incorporate microbes into the very infrastructure of our lives in ways that are concordant with 21st century insights and technologies, offering a whole set of transformations that potentially change the livability of space. So I'm going to start with the Living Architecture project, which I coordinated, and I'm going to share some variations of its manifestations. And then I'm going to propose what scaling up microbes means for addressing shared challenges and establishing a culture of life. Now, the Living Architecture project doesn't do any of this. It doesn't kill our microbes dead. It is a combined utilities platform that uses the vital metabolic activities of microbes, such as feeding, metabolizing, excreting, and reproducing, to establish a circular economy of the household. So offering an alternative resource and energy system than fossil fuels, it carries out housework, cleaning wastewater and producing small amounts of electrical energy, but also acts as an active site for active transactions between humans and non-humans. Now, the basic types of homes we constructed and provided for microbes were three types. So there is a photobioreactor in the middle there, microbial fuel cell to the left, and synthetic consortium to the right. And they were sequentially configured within an apparatus about the size of a large bookcase. And end-stage metabolic products from all these, let's call them little homes for microbes, were then used as food for the microbes next door, whose own unwanted products then went on to feed their neighbours and so on. So being self-contained homes, then that meant that they could process these products sequentially to become metabolic apps. And that enabled a whole choreography of sustained transactions where opportunities arise for microbes to respond to and influence outcomes. So as both a vital thing and an inhabited structure, the inconstituent metabolic processes in this apparatus really are not obvious to us, but they respond to our multiple acts of care through the quality of housework they perform. And they create the possibility of interdependencies that enable environmentally engaged ways of living through regenerative transactions as a technical embodiment of the ancient relationship between a person and their land. So rather than a plot for tender being outside the home, the Living Architecture project technologically internalizes and micro-miniaturizes the soil. Architecturally, it also invokes the same figure and ground that invokes the production of architecture, and the acknowledgement that people are not apart from, but are integrated into the flows of natural ecosystems. So living architecture doesn't provide all the power and resources needed to completely support modern lifestyles. In fact, it establishes limits on resource consumption within our homes that makes us think about how we use energy and resource, marking the start of an innovation process that explores the potential for lower power devices and convergent energy systems. It aims to help us work smarter with household resources and increasingly empower end users working in concert with microbes to customize their environmental footprint. In this way, it's not only a regenerative utility system, but also a pedagogical device that helps us understand how we can work within a broader resource capacity set by the carrying capacity of the planet. Now, from its outset, the Living Architecture project established diplomatic relations between the human microbial interface and was central to the project to stop synthetically modified microbes, we saw their houses a little bit earlier, from escaping into the environment. Exploring the natural regulatory capabilities of biofilms in the microbial fuel cells, Yanis Zaropoulos at the University of the West of England demonstrated that the pathogenic hepatitis B virus could be removed from contaminated wastewater when the flow was looped back through the microbial fuel cell. In other words, the microbial fuel cell acted like an external microbial immune system. So it has the potential to decontaminate domestic waste streams, and the strategic use of natural microbial intelligence could be a key technical principle for negotiating risky microbial environments. Now, microbes possess a very particular kind of intelligence that reveals a great deal about the environmental health of a place, but it requires ways of understanding what they're telling us. Centered on the microbial fuel cell technology again, the ALICE prototype, which is a derivative of the Living Architecture project, produced a readable communications interface between human and microbe by using the direct connection between the electron flows generated by the microbial metabolism and the digital realm. Translating the microbial data into graphical representations of microbes in a relatable manner meant that inhabitants could start a conversation with, rather than exploiting microbes, to help us live together and equitably share household resources. So what might something like this look like? Well, this is a version of the technology based only on microbial fuel cells, and it was developed as an installation to explore the possibility of a post-human apartment powered by microbes and haunted by digital figures or ghosts. It promoted discussion of alternative futures for the household based on microbial platforms. So the next steps are to scale the microbial systems up to make optimal use of waste recycling, which can be accessed through bioelectrical systems. Imagine, for example, if public wastewater gardens were quite literally power plants, where people can go to charge their mobile phones, have free access to online services where LEDs provide street lighting, and all powered by community effluent. And other possible applications range from remediating brownfield sites using smart self-powered sensors and robots, to providing public utilities from urinals that charge your phone or enable you to play computer games, which is already available at Glastonbury Festival. And in the near term, whole settlements may draw on waste to provide an alternative mobile circular infrastructure that leaves almost no footprint behind. So despite their apparent novelty, microbial technology is an old friend with increasing important role in the infrastructural contexts when we're thinking about the strategic importance of communities in managing their resources and the environmental footprints we leave behind in an ecologically stressed world. Thank you very much.
Thank you so much for your inspiring presentation. Let's see if we have some questions from the audience.
Sorted.
So I have one question. So that was very interesting to see how you can, microbes can be, the good microbes can prevent us from diseases such as hepatitis B. So this kind of technology, how much space would it occupy in a building or?
This is a really good question, because I see these as being microbial computers. And if we think about the original computers being the size of a room, that's where we are right now. So the Living Architecture project was about the size of a large bookcase. But with microfluidics, and with a kind of really more strategic interfaces created between the different microbial populations. At the moment, we're using real bulk systems, and we could really cut down those volumes by thinking about almost two-dimensionally about how we put the microbial activities in conversation with our utility systems. So I think there's an awful lot of improvement to be made. This is really a proof of principle prototype, but I also think that these can scale. And so when the wastewater garden you see is actually already built by Organica Inc. I know they've got branches in the States, but they also have them in Europe. And these are wastewater gardens just with plants. Now, our proposal is to put the microbial fuel cells into those so that actually we can have community power-based systems. My big ambition is actually to open up the commons. I'm really not anywhere near as interested in privatization of these as I am in thinking about what this means for public space, what this means for sharing, and what this means for community.
Wonderful. Thank you so much. So if we don't have any further questions, let's move with our next speaker. Our next speaker is Kelvin Yoro. He is a postdoctoral researcher with the Energy Analysis and Environmental Impacts Divisions at Lawrence Berkeley National Laboratory in California. His research interests are in process development, sustainable energy systems, and life cycle assessment. Kelvin, take it away.
Okay, thank you, Jasmina, for that introduction. I'm trying to also share my screen.
Awesome.
Okay, I'm sure you can see my screen. I can't hear anyone. Can you hear me, please?
Yes, we can see your screen. Just make sure that it's in presenting mode.
Yeah, it is at the moment. Okay, so I'll be presenting today on the modeling of hydrogen direct reduction.
Apologies. Yeah, we are still not seeing your full screen. So there is like a button where it says a slideshow.
Okay.
Presentation view, I believe it's called.
Okay. Can you see the screen now?
Not yet. We still see your presentation design view instead of, yeah, that button, exactly. Let's see. Okay. So you're clicking that, but it's not showing. Do you have two screens?
Yes, I do have two screens. I'm trying to disconnect the other screen.
Yeah, maybe. Yeah, you can switch screens. So on top of your view, I think you can switch on which screen you want to have your slideshow, and it's just going to flip.
It's okay. I will just go right ahead to disconnect the screen and the other screen, and then I'll continue.
Awesome. Okay,
can you see my screen now?
We see the screen, but it's still not in the right view.
Oh, okay.
View. Maybe close and open the PowerPoint. Maybe that's happening.
Okay. Thank you very much for the patience. I think I just have some really technical challenges. So today I'll be discussing on the modeling of direct reduction of iron oxide for steel production considering a heat-driven carrier system. This carrier system is a liquid organic hydrogen carrier system where hydrogen is being stored and then also used for the direct reduction of iron. I'm working on this project with my PI and other colleagues from the ANL and the PNL, those are other national labs, and this is a DOE-funded project. So first, just a little background on the iron and steel industry in the United States. It is a good and revenue-generating sector for the United States, but it is also very carbon intensive. It also requires a lot of energy to be used in this process. A rough statistics of carbon footprints emitted from the industrial sector in the United States shows that the iron and steel industry has is the largest contributor of carbon emission so far as of 2020 in the United States. And then to achieve the UN SDG goal on climate change, CO2 emission mitigation, and then energy efficiency, it means that we need to decarbonize the iron and steel industries in the United States. This can be done by profiling technologies that have near zero CO2 emission. Near zero CO2 emission in the sense that because for steel production, as we go proceed on the slide, we will see that it is nearly impossible to have a total CO2 free production of steel, but we can have reduced footprint. Then the iron making process. The iron making process precedes the steel production process. So for steel to be produced, it means we need to reduce iron ore, which is the original raw material. And to reduce iron ore, so far, carbon materials like coke, natural gas have been the major reductants that are being used. And natural gas has so far been the major fuel that has been used to power the process. However, it has been identified that direct reduction of iron ore using pure hydrogen or pure natural gas that is also, of course, has to be reformed to process iron ore steel. To process iron for steel production is still very, very important. So this is the conventional process where coal is being used in the coke oven gas and then used for iron making. So our suggestion here for this study is to replace this blast furnace with a DRI furnace. The DRI furnace is a direct reduced iron furnace where hydrogen will be used. So in this case, we are trying to replace the existing technology with a hydrogen and a more cleaner technology. So so far this will be what we'll be looking at. First, our hydrogen that we're proposing will be generated on site via electrolysis, and then we have our liquid organic hydrogen carriers to store excess hydrogen, and then for future use within the process. We'll look at the potentials of waste heat recovery because our liquid organic hydrogen carriers are driven by waste heat. We need waste heat at some point. We need high-grade heat energy at some point to dehydrogenate hydrogen out of the liquid organic hydrogen carriers. Then we'll also look at the trade-off by comparing this proposed process with the existing process and also another process. Then we'll look at the cost involved by including storage. This is the whole system concept where electrolysis is used to produce hydrogen, of course. The electricity used in the for the electrolysis process is green electricity, is a renewable electricity from wind and solar plants are situated in Southwest Texas. Then the hydrogen is now being stored in our liquid organic hydrogen carriers that is made of toluene and methyl cyclohexane. Then waste heat from the process is being used to dehydrogenate the hydrogen here to gain more hydrogen for use in the DRI furnace and then electric arc furnace, of course. In this particular study, our electric arc furnace is also integrated on site with the entire process. Before now, the major hydrogen carriers that have been used are compressed gas systems and the cryogenic liquids. But in this particular study, we are focusing more on liquid organic hydrogen carriers, as I said, the methyl cyclohexane, where we just apply the principles of hydrogenation and dehydrogenation to make efficient use of hydrogen. Okay, this is a look of what the liquid organic hydrogen carrier system looks like. We hydrogenate, after producing hydrogen from electrolysis, we hydrogenate the toluene system to be able to store hydrogen in methyl cyclohexane. And then for this particular hydrogenation process is exothermic. It means energy is being released to the process and can be used in other parts of the process. However, when we want to now eventually use the stored hydrogen in this system, we have to dehydrogenate at a very high temperature of 350 degrees Celsius. And it's highly endothermic. It means we will need high-grade heat to be able to discharge more hydrogen from our carrier system. So this is where the waste heat comes in. We will now use the waste heat from our process to be able to dehydrogenate hydrogen for use in the iron and steel facility. The basic approach we applied here is just the simple modeling approach, where we gather assumptions. Based on the assumptions, we develop a storage model, we impute data. But for this particular assumptions, we got our assumptions from, of course, literature studies, and also, most importantly, from industry stakeholders, where we had to discuss with Midrex. Midrex is a giant iron and steel industry based in Charlotte, North Carolina, where we had extensive discussions with process engineers from Midrex to understand their process and be able to optimize and retrofit it in with respect to hydrogen. The basic unit operation in this particular case is the DRI furnace, and these are the simple chemistries occurring in the DRI furnace based on the technology we are using. If we are reducing iron or using natural gas, it means that it is really exothermic, and then it supplies a lot of energy. But using hydrogen based, it is endothermic. It means we should be ready to supply heat to be able to power the DRI process. So for our storage, our LOHC system involves hydrogenation and dehydrogenation process. This is the section for the hydrogenation process, which involves mainly toluene. These are the parameters here. And then here you can see that we have heat rejection. It means that it is actually exothermic, and then more heat is being rejected to the process. And then for the dehydrogenation process, this, instead of having heat rejection, we need high grade heat to be able to power this, to be able to also discharge hydrogen for use in the steel process. So now this takes us to developing a process model. So we looked at developing a process model for, okay, we are reducing iron ore for steel production using hydrogen, but we looked at it in two extreme cases. In a case that, okay, our electrolyzer from the grid electricity is able to power this electrolyzer and then discharge about 200 metric tons per day of hydrogen. We need 200 metric tons per day to be able to produce steel. So in this case, our electrolyzer is able to power to produce that amount of energy of hydrogen, and also able to store an equal amount of hydrogen in our storage system. In this particular case, it's an extreme case where we assume there is no electricity from the grid, in cases where there is no solar and there's no wind. Or it means that all the 200 metric tons per day of hydrogen needed for the process must come from our storage. Here we employ dehydrogenation to get all the needed hydrogen, and here we apply hydrogenation to store the hydrogen. Then this takes us to some very few interesting results. We looked at comparing the two processes, comparing the hydrogen case. This is the hydrogen scenario, where we labeled it as case 1 and 2, case 1, A, B, and C. Case 1 is what I showed you, where we had electrolyzer storing and also producing hydrogen, and then there is storage. Case 1C is the extreme case, where there is no electrolyzer. We can see that the first case requires a lot of more electricity, because it needs to be able to produce about 400 metric tons, 200 for storage and 200 for use. In this case 1B, we just assumed there is supply maybe 100 metric tons from electrolyzer, 100 metric tons from storage, and this is entirely from storage. The electricity demand here is really very low, because there is no electrolyzer, and then the only electricity usage here in this particular case is in the compression of the gas, which we also source externally. Then looking at the energy consumption and the DRI production. Okay, in this case, the DRI is a direct reduced iron. It is the iron sponge that is needed for steel production. So how much iron sponge is produced, and how much energy do we need to produce that? So we can see that we produce more iron sponge by using lesser energy. But in the extreme case, which is not really favorable in our own case, we had to use more energy and then get the slightly lower amount of iron sponge which is needed for steel. Then another important thing we looked at was the CO2 footprint. This is a direct carbon footprint. We are yet to carry out the life cycle assessment to look at it deeply. So we noticed that the hydrogen, direct reduction using hydrogen is less carbon intensive. Although it is not zero carbon, it discharges some CO2 because in the DRI furnace, we have to introduce some amount of carbon for carburization. And also in the EAF, we need carbon there to maintain the temperature. And also the component of steel, of course, is carbon and steel. We need some amount of carbon in iron to be able to produce steel. So that explains why it has this level of emission. But in the normal case operated in mid-rex, which we call the business as usual case, where only natural gas is being reformed and the reformed gases, that is CO and H2, is used for reduction, we had this very high CO2 emission. Then we had to look at trying to supplement this business as usual case by adding hydrogen to the natural gas process. It drops down the emission significantly, which shows that the addition of hydrogen, supplementation of hydrogen to the existing process could actually reduce carbon emission by a very, very far margin. Then we look at also the efficiency of the process based on the amount of steel each process could produce. The least efficient process, of course, is the most carbon intensive process, which is the conventional process being employed currently by Midrex. So we looked at the waste heat recovery options. How do we get heat to produce, to dehydrogenate hydrogen into our process? Having taken the heat duties of all the unit operations, we were able to figure out that the EAF off-gas stream and the waste gas coolers have the highest potential points where we can get the needed amount of waste heat. So we're able to capture our waste heat from those particular units to recycle for use in the process. Also, how much iron sponge did we get from the process and how much steel is being produced? For the hydrogen case, this is the amount we got. Then this is the conventional amount where the total iron ore produced is actually more. And because in this case, remember, in this case, we're reducing with just hydrogen. In this particular case, we have hydrogen and then CO. CO is also a reductant for iron ore. So it means we need to charge in more iron ore feed to get more iron sponge. In this particular case, we have to get more than the rest because in this case, we have the normal CO and H2 doing the reduction, but we supplemented it with another 200 metric ton of hydrogen. So we had more iron sponge to reduce and more iron ore to reduce and more iron sponge to produce for steel. Then we try to play around with the composition of the reduced gas, the CO and the H2, to determine its effect on the thermal, on the energy demand of our process. Then we're able to find out that because normally, conventionally, in steam methane reforming, we have more CO to H2. So if we decide to reduce the composition of CO in this case, and then increase the hydrogen, it increases the energy demand and it also increases electricity requirement. So ideally, and also looking at the amount of iron sponge that could be produced, it means that we need to operate at these because the more we reduce the CO content and the hydrogen content, the amount of iron spore declines gradually as well. Then finally, before we conclude, we'll also look at another important factor, which is water consumption, because electrolysis requires water, steam methane reforming requires vaporized water as well. And then also in the DRI process, a lot of water is being discharged, because when iron is being reduced by hydrogen, water is a major final product. So we're able to characterize this. For the hydrogen case, where we have just electrolysis and the DRI itself, this is the water requirement. In this business as usual case, the mid-rest process, which we use to benchmark our process, they do not use electrolyzers, just the DRI and the steam methane reforming. That is where the water demand is. But when we decide to supplement with hydrogen, it means we need to bring in our electrolyzers to generate hydrogen. That is why we also have some water demand, water footprint from electrolysis. On the overall, when we supplement, we tend to use more water than when we use the conventional, the new hydrogen, pure hydrogen case. This means that if pure water, if distilled water is being required in the electrolyzers, it will slightly increase our process cost. Hence, we have to include a purifier in our process, then just to be able to purify the water discharge from the DRI and then recycle it back into electrolysis. Also, by introducing a storage system, a liquid hydrogen carrier storage system, it means that the process cost will actually increase. So we're able to determine the total cost of ownership for storage of hydrogen using our methyl cyclohexane and toluene system. We determine the capital expenditure, operating expenditure, and the total cost of ownership. Then to conclude, these are the major findings. First, we need hydrogen storage to be able to meet the needs of the iron and steel industry, because when this hydrogen is produced, hydrogen is a very, very important gas, important fuel, and we don't need to waste it. So we need storage, but it also increases our process cost. We need to be able to optimize the process efficiently to reduce this cost. Then also, we also find an important take home that carbon-free iron and steel making is very, very unlikely. But we can also reduce the amount of CO2 that comes from our iron making process and steel making process by introducing the use of pure hydrogen, or then supplementing the existing process with hydrogen. Then also, there is a potential to recover waste heat. It means that we don't need to buy heat energy to be able to run our storage system. And at the current electrolyzer prices, these are particular total cost of ownership is possible, but then not without some few challenges. Then finally, we're able to conclude, if we can able to run a total cost of ownership for the storage system, there is a need to also run a techno-economic analysis for now the overall system, including the DRI, the AAF, the storage system, just to be able to determine the financial viability of our proposed processes. Thank you very much. I would like to acknowledge the Department of Energy through the Hydrogen Fuel Technology Office for funding this research, and then Midrex that for providing technical support, and then our collaborators from Argonne National Lab and the PNN National Lab. Thank you very much. I'll be happy to entertain any questions, and then also any comments. Thank you.
Thank you so much for your presentations. Are there any questions first from the audience?
Yes.
Go ahead.
I wanted to ask you something. You're trying to replace the conventional steelmaking process with the DRI, right?
Mm-hmm. Yes.
So in this process, you're trying to replace only the cocoa ovens, not the sinter units, right? So if that is the case, we might have sinter heat as well as the blast furnace gas, which is released in enormous amounts. But in the whole presentation, I haven't seen such factors or such gases in the waste recovery units.
Okay. I think to answer that question, that is a very interesting question. First, this particular study is trying to replace the blast furnace itself. We don't want to use the blast furnace in this case. We want to use the DRI. So most of our gases and products comes from the DRI, not the blast furnace. So it is what I'm saying in essence is, now imagine a process where a normal process where the BOF is not there, then the DRI is there. So that is why you were not able to see those particular aspects. But in the conventional processes, it's normal. It's business as usual. The BOF is there. And this is also a work in progress. We're trying to include a lot of things in it. And that is why I will really be happy if I can get very, very good more suggestions on how to improve on it.
Yeah, maybe we can use the circular energy supplies option here, because your electrolysis units consumes a lot of DC electricity, right?
Yes.
And in the real world scenario, we don't produce much DC. So more or less, we are with AC, and converting AC to DC again is another big infrastructure we needed. So maybe you can think of circular energy supplies using this waste heat recovery options itself.
Oh, okay. I think that is a very good consideration. But at the moment, what we do is we own the grid, the renewable grid, the wind and solar plants. We own them, so it is not what we buy or what we bring into the process. It is on site, and then we just directly from there get our electricity. But I think for comparison's sake, this is also a very good suggestion. I think I will also have to look into it deeply. Thank you very much.
Thank you so much.
Awesome, wonderful. Thank you to our speaker. So next, our next speaker, we have maybe one more question.
Kelvin, I do like your job, good research. I prefer hydrogen reduction steel making, as I said in my presentation. And I want to ask a question. Can you describe advantages and disadvantages comparing with, just I said, electrolyzing steel making, like that comes from Boston metal, as my slide shows. Can you describe that?
Okay, I think if I really understand that question, you're trying to know the advantages and the disadvantages of our process compared with the conventional one, right?
Yes. I think the main difficulty in electrolyzing, direct electrolyzing steel making is the inert anode, because that method need a very high temperature, 600, more than 600 degree. If you use hydrogen, hydrogen can come from electrolyzing water, or come from methane, CH4 or C2. That can be made in with very lower temperature.
Yes, of course.
I think it is feasible, the most feasible because of the temperature?
Yes, that is a very great question. I think I understand it clearly now. So for this particular process where we generate our hydrogen from electrolysis, before it goes, if I go back to my process models, you will see that before the hydrogen goes to DRI, we have to preheat it to a temperature of 900 degrees Celsius. And that is why that is what contributes to the energy demand of the process. So it doesn't go directly at the temperature from the electrolyzers. It has to be preheated. And also remember that in the chemistry of the DRI, ion reduction occurs in stages. Some stages are exothermic, which also supplies heat for the DRI. So at the end, the DRI operates adiabatically. So we don't need to, the only source of heat to the DRI is the gases, and that is why we had to preheat the gases. In the end, our ion sponge has to come out at a temperature of about 700. Midrex gave us a range of 700 to 900, and then we're able to come up with a range of about 730 degrees Celsius, which was acceptable by them. So what entails in this particular case is make sure before reduction, both the CO in terms of the natural gas case, both the reducing gases, that is the reformed gas from the reformer, has to be preheated. And also, we also added methane in both processes, just an oxygen, just to supply heat in the process. The oxygen is being gotten from electrolysis as well. Instead of wasting that large amount of oxygen, we try to take a little amount, send it to the DRI just to supply that needed heat, and then bring it out at that particular temperature. So I think if that answers your questions, that is good. Otherwise, I'll be happy to still talk after this.
Thank you so much. Thank you so much, Kelvin. And thank you for all the questions from the audience. But we have to move to our next speaker. Our next speaker is Nallapaneni Manoj Kumar. He is a PhD student at School of Energy and Environment, City University of Hong Kong. He has submitted his thesis, congratulations, and the title is Leveraging Blockchain and Smart Contact Technology for Sustainability and Resilience of Circular Economy Business Models. Nallapaneni, take it away.
Can you all see my screen now?
Yes, perfect.
Yeah. So I think, thank you for the introduction. I think she covered almost a little brief introduction about me. So today I'm here to talk about a topic, how to design microgrids in line with Sustainable Development Goal 7. I think even in Kelvin's research, he has a microgrid with solar and wind configurations. Somewhat similar here also, we have a microgrid configurations. But more or less, I will try to design this microgrid considering different indicators of SDG 7. Now, the most famous indicator in terms of electricity access, electricity supplies around the globe we have is electricity access. So the share of population having electricity access is different in different countries. And if you see this graph, we can see a clear difference between the Western countries and the Asian and the Middle East countries. So more or less, we can say that the countries that fall below the bread line are having lesser energy access. So that means the countries in Global South are not having access to electricity. So is it only about electricity access we should talk, or is there any other indicators we need to include while designing such energy systems? So let us see what SDG 7 says. So SDG 7 is more or less informing us to have energy system that is affordable and it can also provide clean energy. And it has a set of targets. So the first target is about ensuring universal access, whether it is a global north or a global south. the energy should be affordable, reliable, and modern. And 7.2 is to increase the share of renewable energy. This is more again talking about the sustainability aspects of energy supplies. And 7.3 is about improving energy efficiency in a way we use our electrical infrastructure. So more or less, the most electrical appliances we use are not highly efficient, and they consume more amount of energy. But SDG 7 suggests us to move towards using energy efficient devices. And we have two other sub indicators, that is 7.A and 7.B, which are more related to research and technology, and how do we upgrade our existing infrastructure and technology. So now let us see how these countries performing with SDG 7. Now, if you see this particular figure, so even in the countries in Western world were not achieved SDG 7 fully. So though Canada and few of the South American countries have fulfilled their SDG 7 targets, but rest of the countries, even in European Union and few of the countries in Northern America, still have minor challenges. But if you see the global South countries, they have major challenges. But there are two other countries that fall under global North. Though they are well developed, they still have challenges. For example, US and the Australia. So though they have 100% access to electricity, but their SDG 7 still remains more or less similar to other countries. Maybe the main reason here is they're more dependent on fossil fuels, or they might not have reliable power supplies. So the questions about having a power system that is more reliable, affordable, and also whether it is modern energy services are offered or not is a big question. Now, when we see these challenges, the challenges faced by global South are more when compared to the global North. Now, taking India as a representative country for global South, I know India cannot be a full-fledged representative, but I just wanted to use Indian case to show how global South is improving in terms of their energy infrastructure and all. So let us see what India is doing in terms of electricity providing to its people. So as of now, electricity access percentage in India is 99.6%. And around 5.5 million population doesn't have access to electricity. But when we see the access levels, it has a very high accessibility. But what are the other parameters that are affecting the total Indian power sector? So those would be reliability, affordability, and sustainability. Now let us see what India is doing in terms of its sustainability. So when we see the statistics between 2009 and 2020, India has put a lot of efforts in increasing its renewable energy share. So if you see the current statistics, the renewable percentage is increased by 4.9% in last year itself. And this has resulted in reduction of fossil fuel usages. Even energy efficiency standards were improved. Due to that, the energy demands were reduced by 2.7%. So more or less, India is contributing to sustainability in terms of its national energy mix. But still there are other challenges. So this means that sustainability is not alone the issue anymore. So what could be the other issue? Now, when we see the recent published literature, one of the article published in Nature Energy in 2006 have clearly mentioned that the energy transmission and distribution has a major losses in the total power sector of India. In addition, there is a power theft happening at different stages. And on the other side, when we see the household satisfaction of electricity supplies in rural India, they were not satisfied. This is due to longer power outages and also unreliable power supply, and more or less we see low voltages in remote villages. And we see a recent news published by Financial Express, and average electricity power outages were cut down to few percentages, but on average, they are 18.37 hours to 17.17 hours. But we see the total India, the power outages scenarios are referred like this. The least power outage duration we experienced is in Uttar Pradesh state of northern India, that is 0.6306 hours as it's an annual average. But when we see the highest, it is in southern India, the state called Tamil Nadu. So we have average power outage duration is 25.94 hours. So which is really quite high, almost a day. So now what could be the solution for this? And one of the modern solution in terms of SDG is the microgrids. So a definition given by US Department of Energy for microgrids is a microgrid is a localized energy grid with control capability, which means it can disconnect from the traditional grid and operate autonomously. So as we're talking about the issues of reliability and power quality and all, so it is always better to have a system that can operate on an isolated mode. So though if we have any fault on the total power infrastructure side, the total Indian grid system, but still this microgrid can offer a reliable energy service to its consumers. And microgrid is otherwise called as self-sufficient energy system that serves a discrete geographic footprint, and it can be powered, it can be used to power a residential building, office building, even an industry, or any sort of neighborhood, or even like communities. Now let us see how a microgrid architecture should look. So I think this is a typical architecture of a microgrid, which unites all distributed energy generation technologies and the transmission and distribution system at a local level. And it can be even integrated with different energy storage devices, or even the most trending EV concepts. So that concepts can be called as vehicle to microgrid concepts. So now let us see the objectives what we have here. So the primary objective of this study is to design a microgrid in line with SDG 7. So the first objective is to develop a framework that considers SDG 7, the four key criteria. And the second objective is to model a microgrid considering various distributed energy technologies for a household community, allowing reliable and continuous power supply throughout the year. That means a 0-hour disruption. And the third objective is to carry out techno-economic and environmental optimizations for selecting the most feasible microgrid configuration in the context of SDG 7. So now, considering these objectives, we have formulated a case study, and that case study is considered the highest power outage recorded in India. The state, Tamil Nadu, which has recorded almost more than a day, the power outages. So we have considered one village in the state where electricity access is quite lower. So as a sample study, 12 houses were considered, and we assumed that these 12 houses will come together to form a microgrid. And before proceeding with microgrid planning, we have estimated the electricity loads of this particular houses, and we observed that a variation between 0.58 kilowatts to 1 kilowatt. And we have chosen the technologies like solar, wind, battery storage, and diesel generator. So the reason for choosing battery storage and diesel generator is to ensure that the system is reliable and resilient. So as it is a grid independent system, so if there is any disruption, if there is any failure at the generating unit itself, so we need to have a backup systems. So for that reason, we had a primary backup system that is battery, and in the worst case scenario, the secondary backup system, which can give an immediate power supply, that is a diesel generator. So now let us see the framework. So for designing this framework, what we did is we have combined the knowledge of Sustainable Development Goal 7 and the knowledge of microgrid, how these microgrids are seen from a consumer aspects or a prosumer aspects. So the knowledge from the two subjects were combined to explore different indicators. Now, when we see this SDG 7, the 4 criteria: affordable, modern, sustainable, and reliable. I think microgrid itself is offering modern energy services, so we no need to think much of this modern aspects. But there are other 3 criteria: affordable. So all the financial indicators, that is offering electricity at lower prices, and the investment should be lower, and also the net present value should be lower. So these indicators were considered and grouped under affordable category. Then in terms of reliability, we have like continuous power supply, and there should not be energy shortage, and even power quality should be ensured. That means the voltage level should not be dropped, and it should not fluctuate. So that sort of conditions we have considered under reliability. And under sustainability aspects, we consider that the higher renewable energy fraction and lower emissions. So as we are using diesel generator as a backup, we cannot guarantee that a zero emissions would be there. And even from a life cycle perspective, zero emissions can't be achieved. So that's the reason we have used an indicator called minimum emissions. And now, so these are the methods. I think most of you are familiar with this techno-economic and life cycle methods. And so, but let me run down through the TEA we have done here. So the TEA we have done is combined with optimization models. The LCA doesn't include any of the optimization models, but however, it directly considers the optimized model from the TEA, and we perform the cradle to gate analysis in LCA. But let me give more brief information about the techno-economic assessment methodology. So the first step is we had like initial problem assessment. The problem is of power outages, and we need to ensure a reliable and continuous power supply throughout the year. So then we have gone for a pre-assessment. So this pre-assessment mainly includes the resources. The resources means at the geographic condition levels, what could be the renewable potentials like solar energy potentials, wind potentials, and the electricity demands, or how the electricity patterns are varying from house to house. Then what sort of system we need to design, and if so, how many types of configurations we can have it. So it's all based on the probability. So we run an optimization model here to see that how many configurations are possible. And from the pool of configurations, how we select one configuration that fit with SDG 7. So now for this, after this, we conducted the techno-economic assessments, and then we even carried out the sensitive analysis. And the life cycle assessments is accounting the emissions from cradle to gate. So we have not considered the end of life emissions here. This is because the components we used here have different lifespans. For example, the battery lifespan may not be equals to the lifespan of the photovoltaic modules or the wind turbines. So that's the reason we have not included this end of life modeling here, but in the future works we may include it. And these are the few conditions we have taken. The resources required for the assessment are collected from the NREL databases, and the load data is collected from the residential buildings based on their electricity bills, what they pay to the Tamil Nadu government. And then we have used a controller called load following controller. So this controller will allow us to ensure that a reliable and continuous power supply is ensured for that particular given load. And also, this controller will allow us to ensure the operational flexibility of different devices we have in the system. And then we used a single objective function, that is the least lower electricity prices. So we have optimized to have a configuration that have a lowest electricity prices. So that considers the single optimized function, and the emissions are cradle to gate, and the functional unit is kilowatt hour. So as a first step, as I mentioned already, it's the resources. So for this microgrid configurations, we have considered solar and wind are the potential distributed energy technologies. So that's the reason we have gone for solar radiation potential assessments and wind speed potential assessments in the particular locations, what we observed is the location has an average of 5.12 kilowatt hour per meter square, and its clearness index is 0.52. The clearness index mainly tells about how the cloud cover exists in the particular location. And the wind speeds range between 2.2 to 3.45, and the average wind speeds are 2.75. And now coming to the step 2, that's the load patterns. So in the first graph is explaining about how the load pattern is varied in this particular community on a daily basis. So here I have showed a typical day load profile that is recorded on 22nd April 2017. Though the load profile is little older, but still we have used it. And then later we have analyzed the load profiles considering seasonal variations and the time-to-time operation of their electricity devices. And what we observed is the load is changing at different months at different patterns. But more or less, the peak load we observed is 20.46 kilowatts, and average load is 6.89 kilowatts, and daily energy demand is 165.44 kilowatt hours. And now, while designing the microgrid, what we had to consider is we cannot just consider the average load. So we always need to consider the peak load. So if we design our system for a peak load, that means it can withstand even for any sort of load disturbances we have, even for plus or minus some percentage variations too. And now the next step is the system design. So as I mentioned, the first we have already assessed the resources, then the load, now the system configurations. So as I mentioned, we have run the single objective function models considering different combinations of this distributed energy technologies. And based on the optimization results, what we have is we have observed a pool of feasible microgrid configurations, and we arrived at total 132 feasible solutions. That means, so that different solutions are possible, but out of all, only 132 solutions are feasible. But now, out of these 132 solutions, how many solutions would be better fit when we do sensitive analysis having upper and lower bound of few parameters? So for that reason, we have considered a few technical parameters and few economical parameters here, and few parameters that that influence the power generation process directly. Let's say now we have a solar power system also here. So that's the reason we have considered a sensitive variation of solar radiation that is 5 to 7 and wind speed between 2 to 4. And considering the India's situation, we don't have any control of the fossil fuel prices. Most of the crude oil we get is imported from other countries, especially the Gulf nations. So the price is fluctuating. So that's the reason we have considered diesel fuel price as a sensitive parameter, and the nominal discount price for such renewable energy projects is again considered as a sensitive parameters, varying between 5 to 15%. Now, when we further run the optimization model, what we observed is we arrived at these 4 configurations. That means a total 4 microgrid configurations were found to be feasible based on the sensitive analysis. And here the DZ represents the diesel generator, BES represents the battery energy storage system, and PV represents the photovoltaics, and WT represents the wind turbines. Now the further conditions is how do you filter these 4 sensitive cases and to pick the final configurations that will fit under SDG 7 criteria. So now all the results we have shown here. Now a comparative assessment of different indicators we considered as per the SDG 7 criteria and the overall SDG 7 goal. So all the indicators were mapped here. Now, if we see the indicators and if you see the SDG 7 knowledge, what we need to have is we need to have an affordable system. That means the price should be lower and it should be reliable. That means there should not be any power shortage and it should be sustainable, lower emissions, and it should be modern. I think modern is, by Microgrid itself, is allowing the modern energy services. Now, if you see the last two configurations, we can clearly see that the electricity prices are quite higher when we compare with the previous other two cases. That means this is not affordable. And now when we see the reliability parameters, so here we have only the battery as a primary backup source. But what if the battery fails? And if you wanted to have higher battery capacities, maybe the unit price cost of electricity would further increase. And in addition, this is producing huge amount of excess electricity. And this is a grid independent system. We don't have an access or a provision to trade this excess energy. That means this excess energy will be considered as a waste. And in order to store this excess energy, we need to invest a lot on battery infrastructure, which is again increasing the total capital investments we made it. And on the other side, considering the intermittent nature of these renewables we have, because in these two configurations, we have only solar and wind turbines. So solar and wind potentials are not constant throughout the year. So they might vary and they might fluctuate at different ranges. So we have power shortage and the capacity shortages. That means from a reliability point of view also, these two configurations will not fit. And the other side, we have a lower emissions when we don't consider the life cycle emissions. This is because we don't have any diesel component. Because if you have a diesel component, diesel fuel will be burned and we have a direct emissions, but there's no such scenario here. But when we see the life cycle emissions, considering the solar capacities, wind turbine capacities, and the battery capacity that is needed to store all this energy is too much. So we have like the life cycle emissions are really higher, but we have a higher renewable energy fraction because there is no other fossil fuel component, and whatever energy we get is all coming from renewable. So renewable energy fraction is really high. But we cannot provide energy access to all because still they still have a power shortages here. So that means these two configurations were doesn't satisfy the SDG 7 criteria. So now the only options are the rest two. So let us compare the rest two options. Now, if you compare these two options, what we could see is more or less the cost of electricity is similar. But when we see the total capital cost, the capital cost in second configuration is really high, and this is because of the wind turbines we have. And in addition, both are generating a similar amount of excess electricity, but when you compare this electricity to other configurations, we can easily store this in batteries. So that's the reason we have battery as a primary backup system. And other side, we don't see any sort of capacity shortages here because as per the control technology we used here, even when there is an intermediate nature with this solar and wind, a diesel generator can be on immediately for a shorter durations, and the power shortages can be minimized. And the other side, because of the diesel consumption, we have few emissions. And however, when we see the total life cycle emissions for the service life of all the components, the emissions are quite lower when we compare with this other two configurations. But however, on the other side, we have a renewable fraction of close to 80%. So the main reason here is 20% is contributed either by battery or diesel. But on the other side, we don't have any capacity shortages or power shortages. That means a system with wind configuration does not really fall under SDG 7, but the system with PV, DC, and battery will be better fit for SDG 7 criteria. And now let us see the performance analysis of the selected configuration under SDG 7. So now, as I already mentioned, that this has only 2 generating components, and here we see the generating component, that is a solar power plant. Now here I have shown the trade-offs between solar radiation it received and the amount of solar power it is generated. So more or less throughout the year, we have solar potentials, but there are few exceptional cases where solar radiations are quite less and the cloud cover might be high. So in those conditions, we have lower power outages, lower power outputs. But and overall, the capacity factor of the solar power plant is close to 24%, which is really a higher percentage when we compare this with other states in India. And now, so as we already mentioned that due to intermittent nature of renewables, in some days, solar alone cannot be used to meet the electricity demands. But in some instances, we have excess generation from solar. So now here we have shown the battery operation. So whenever the situation of deficit energy is there, battery tends to discharge. Whenever there is an excess energy, it is stored in the battery. And a similar patterns is observed throughout the year. And more or less, what we observed is the battery never run at its depth of discharge levels. And more or less, we have a constant state of charge levels. And now, in the worst case scenario, so we have a secondary backup source, that is a diesel. So we have seen some instances where we have run the diesel generator to meet the power demands. And once we see that an annual, we have a diesel consumption of 4,000 liters close to, and the specific fuel consumption is 0.36 liters per kilowatt hour. And the diesel generator had an efficiency of 27.7. And so what we observed here is this configuration is in lines with SDG 7 goals. So though we have a fossil fuel source in the picture, but it is used as a resilient measure itself, considering the location that does not have an access to hydropower plant or any sort of energies. And now what we have the conclusion points here is the proposed framework and the indicators selected were useful in making decisions regarding microgrid design in the context of SDG 7 in the global south. And the same framework may be applied in other countries or regions as well. But however, the same configuration, what we come up here, may not produce similar results in other regions. Hence, it is always suggested to have a microgrid model specific to geographic conditions. On the other side, this study does not account for end-of-life benefits of photovoltaics and batteries from a circular economy point of view, and this can be a future work. On the other side, we are even looking at expanding this model, considering fuel cells into a picture, biomass, electric vehicles, and other storage systems. And here the fuel cells does not mean only the conventional fuel cells. We are even looking at the fuel cells that can run on hydrogen that is generated from the wastewater, etc. And now the session is open for questions. Thank you.
So unfortunately, we don't have time for any questions, and it was our decision to postpone Bensu Manav's presentation to the session tomorrow, because I really want her to have a chance to talk to a broader audience. Many of the people have already left for lunch. So with that, please keep in mind to keep your presentations within the proposed time, because we want to avoid this to happen to other people.
I'm sorry.
So with all that, I take all the presenters and audience to joining this session, and enjoy the rest of the day.